All right, good afternoon and welcome to session 3. I've titled this session as Getting Started in the AEI Toolbox. So we're going to talk about how you actually begin doing a power supply design. And this is going to be part 1. I realized that to cover all of the stuff that falls under this category would run much longer than an hour, and I wanted to keep the sessions to an hour just so it's easier to absorb the information. So I am Larry Crosby. So here's our agenda for today. Got a little overview. We'll do some review about gathering data, and then we'll talk about the tools that are available for doing power design at ADI. We'll do some detailed look into creating a power tree. And then part 2 is going to really address this power design step, although we may touch on it at the end of this session. So let's get started with the overview. You've been to session 1. We talked about power fundamentals and awareness. Session 2 was introducing the different types of converters and integration levels. And we talked in a little more depth about LDOs and switchers. And session 3 is where we are now. So we're going to talk about how we get started and the tools that are available to help you. Gathering data is still the first step, the power requirements. The requirements are, what's your input look like? How many rails do you need? What are the voltages and currents? And are there any special rails that need closer attention? The priorities are how we implement it. The requirements are the numbers of what we need. The priorities tell you how, what you should prioritize when doing the design. So size, efficiency, noise and ripple, transient response, and cost. You really want to try to list these in order of importance so that you know what's the most important aspect and what's next and next, and what's down at the bottom that isn't as important. Then after you gather all this data, you need to do a little interpretation. Are the priorities logical? Are they achievable? If I want to have, a 98% efficient power regulator and it's got to be really, really cheap. Well, those are sort of mutually exclusive so that they're not really achievable at the same time. It's kind of, you can have one or the other, and depending on which is more important, the other one's going to suffer. And the other question is, should we provide choices for solutions? Maybe if not sure about priorities, maybe you provide a plan A and a plan B where they both can get the job done, but one may do a better job for one priority and another one may do a better job for another. Okay, tools. So we have a number of tools available to help you do power design. I'm going to show you some of the tools that were developed at Linear Technology. These aren't the only tools we have, but it's a fairly comprehensive suite. So we'll take a look at that briefly. The first is called LT Power Planner. This is a tool for creating power trees, doing some basic analysis on how much power is going to be used by each of the converters and each of the loads that you have. And this tool does all the math sort of behind the scenes. So it'll keep track of this converter has an efficiency of some number, 90%. That means that 10% of the power gets lost. So the tool will take that into account when it looks at how much power you have to deliver from your input source. It also provides nice graphics. The second tool is called LT PowerCAD. And the way this has evolved, LT PowerCAD is now a complete tool suite that includes LT Power Planner as one of the tools in the toolbox. The PowerCAD core includes a search and selection page that comes up when you launch that tool. This allows you to enter in requirements like the input voltage, including the range, how many rails, what are the voltages and currents for those rails, and then you can search for a part that will match or meet those requirements. So that's sort of step one. You need to decide which part are you going to use for this particular rail. And then it has a circuit parameter design phase that you can go through. This allows you to look at the schematic for the circuit, choose the external components that go along with whatever device you've chosen, and it's doing all the math behind the scenes. So it has lots of prompts about, oh, this parameter is getting pretty close to the limit, or, this parameter isn't big enough, you need to make an adjustment. It also can show you efficiency curves and loop response for whatever circuit you've designed. So very powerful tool set there. And the last one is LT Spice. This is a general purpose simulator that was developed many years ago at LT. And it can quickly get you electrical performance of your circuit. And it's a great way to sort of get your arms around how the circuit operates. And you can probe voltages and currents. So, probing currents is a little challenging to do on the bench. In LT Spice, it's very easy. You just put a current probe there and it'll show you what the current looks like. So all these are useful tools, and I encourage you to investigate them. This is a page full of links. The top one is the power management tools. So this is where you can find the downloads for all these different tools. So specific tools, the PowerCAD suite can be found at this link here. There are also quick start guides, both for LT Power Planner and LT Power CAD. There's also some useful app notes. These are app notes that you can download and read. You can read them online as an HTML, or you can download a PDF version. And these are app notes that talk about switching power supplies, and they go into a lot of the higher level math behind how switching power supplies work. They're somewhat theoretical, but there's a lot of good information in there, so I would encourage you to have a look at these as well. Okay, so power tree. What's the first thing we have to do? Well, the first thing we need to do is to gather that data. And so I put together a list here that is an example of what you might gather. So this is a list of rails for the system. From this, I can surmise that the input power is 12 volts. It's coming from some kind of power supply, or maybe it's a power adapter or whatever. Each rail has a name, and then we have the rail voltage for each rail and the maximum current that's expected to be drawn from each rail. And then I have a column here that I like to put in indicating what priority have we used to optimize the design of each power rail. So some of them might be optimized for cost. Other ones, size. Maybe they're in an area of the board where there isn't a lot of space, so we want the most compact solution we can find. Noise might be a factor. In this case, the SerDes rail, we've talked about SerDes circuits, and those are noise sensitive, so we want to optimize that rail for noise. The two core voltages, the FPGA and CPU cores, these are much higher current, and we want to optimize the transient response on those because they're core supplies on these chips, and we know from experience that those chips typically have pretty tight requirements on the deviations from nominal on those rails. And the last one here is called VTT. This is a termination rail for the DDR memory. This is commonly required when you use DDR memory. They need a termination rail that allows you to efficiently keep the transmission line effects from corrupting the data in the transfer of data back and forth from the memory to what other devices are using it. So special rails, SerDes, we mentioned that. So noise is a problem. So for low noise, we're going to use an LDO. Now note that this rail needs to be able to deliver 3 amps. So that's quite a bit of power, quite a bit of current for an LDO. So what are we concerned about with an LDO? Power dissipation. At 3 amps, the power dissipation may get fairly high unless we pay a lot of attention to what's the input to the LDO. So the output is 1.5. If we try to use 12 volts as the input, we'd have a huge voltage drop across the LDO. And with a 3 amp current draw, it's going to get way too hot. So we need to look at how can we minimize that input to output differential on that rail. And in the VTT termination rail, what's unique about the termination circuits for DDR is that they have to be able to source and sink current more or less symmetrically. And that means that this rail needs to be able to source 3 amps, in other words, drive 3 amps into the load, or sink, pull 3 amps out of the load. And the reason that's required is that it's a termination. It essentially looks like a big termination resistor, and the DDR voltage average may be above the VTT voltage level or below it. If it's above it, it's going to push current back into the VTT regulator, and it'll have to sink current. So we need to make sure we choose a device that can do that. So where do we go next? I like to create a sketch of the power tree. It's a force of habit for me. It's not required that you do it. It just sometimes helps kind of get the arrangement down on paper a little more clearly, and you can sort of iterate through this and get things kind of where you think you want them. So I made up this power tree based on that table that we just looked at. And here are the devices that I chose. And, I may go back and revisit these as time goes on. A few notes. Here I chose the LTC 3614. This is a part that's specifically designed for VTT termination applications. Now, one caveat to using this part is it has a maximum input voltage of 5.5 volts. So as a result, I can't run this part directly off the 12 volt input because the input, that's too high for this part. But what I can do is I can use for an input one of the other outputs on the board. So I notice here I have a 3.3 volt rail, and this part, the LT8640A, can handle more than 3 amps. So there's a little extra current available. I could use that to run this regulator, and it solves that input voltage limitation problem. Here's the LDO that I'm going to use for the SerDes circuit. The output is 1.5 at 3 amps. And I've chosen to run this LDO off a 1.8 volt rail that I also have in the system. That means that the differential from input to output across the LDO is only 300 millivolts. And now 300 millivolts times 3 amps means that the LDO will dissipate about 0.9 watts. And that's manageable in a device like this. This device comes in a fairly large package with good thermal characteristics. It has a heat spreader, so you have a easy way to get the heat out of the package. And so 900 milliwatts, just under a watt, is manageable with this part. And so running it off 1.8 volts allows that to work. Okay, so now let's get into LT Power Planner. And in a moment, we're going to go over and actually look at creating a power tree using the tool. But first, I wanted to just share this flow chart. This is, to a rough idea, this is what I go through when I'm trying to figure out how to build a power tree. I'll compile a list of the rails. We already have that now. I'll pick a rail. It's got to start someplace. And I'll evaluate what type of regulator would best be used for that rail. Is it a discrete design with a controller and external FETs? Is it a monolithic part where the FETs are on chip? Or is it a micromodule or an LDO even? So think about what type of regulator you think makes sense for that rail that you selected. Then you have to search for a part. So in a moment, we'll get into how you go about searching for parts. But once you select a part, The next step is to read the data sheet. And that doesn't mean reading every word on every page. The data sheet might be 40 pages. You don't have to spend a weekend memorizing the data sheet, but you need to know the basics about how this part works, what it's designed for, or the types of circuits it's designed for, what are the voltage ranges. You got to make sure it can handle the input voltage range and the output voltage you want. So do some perusing. Certainly the first 6 or 8 pages of the data sheet will have a lot of that relevant information. And you have to make a decision. Is this a good fit for this rail? If the answer is yes, you can proceed. If it's not, or something doesn't seem like it's maybe optimal, go back and look for a different part. So it's an iterative process. Once you find a part that you think is a good fit, it's nice to have an estimate of the efficiency, the conversion efficiency that this part in the configuration you need will deliver. And we'll talk in a little bit about how to get that efficiency. Once you have that, you can enter it in the power tree and move on to the next rail. And you step and repeat until you've covered all the rails. Choosing parts. How do we go about that? You can look for parts on the ADI website. That's one place to look. There's all kinds of selection tables on the ADI website under the power management section. There are thousands and thousands of parts. So part of the challenge there will be to narrow down the list of parts by giving the website information like the input voltage range. How much output current do you need? You can enter some of that information into the search columns and narrow down the list to parts that can actually do what is needed. So that's one place to look. LT PowerCAD is another place, and we'll actually go through this in some detail shortly. And there's another tool called EESIM. This was developed at Maxim, and it has a similar sort of interface where you enter in the basic information about a rail, input voltage, output voltage and current, etc. And then it will show you the parts that match all those requirements. So those are all choices. We're going to look at LT PowerCAD today. So let's shift gears here a little bit, and we'll start by looking at the power planner to create the power tree. When you launch the LT PowerCAD suite, this is the startup window. So it shows you all the different tools that are available and are part of the suite. In many of the parts of this power suite, where there's an icon, if you hover over the icon, a little alert box comes up and tells you what that icon does. It's very helpful. So the supply design icon, it looks like a little chip maybe, and that launches the LT PowerCAD power supply design tool. The icon called system design, that launches LT Power Planner. This is where we create the power tree. And there are icons for the LT Spice simulator, for opening a file. Maybe you've created one already and you came back to it a week later. You can pick up where you left off. There's a signal chain power tool. There's EESIM is there. And there's a toolbox, which has a bunch of helpful files and things in there. And I'm going to open that briefly just so we can get a look at it. And so when we open the toolbox, here are all the different tools that we can look at. There are a number of Excel spreadsheet tools, and there's some PDF files. So here's the LT PowerCAD Quick Start Guide. This is the most updated version. So you can open that up to look at the Quick Start Guide. There's also a Quick Start Guide for LT Power Planner. That's here. So feel free to peruse these at your leisure. So now we're going to go to system design. We're going to start creating our power tree. And when you click on this icon, you'll get a blank Power Planner window, which looks like this. So this says LT Power Planner. There's a version number up here. And there are a series of icons across the top that do all sorts of different things. And again, as I mentioned, you hover over an icon, a little box comes up and tells you what that icon does. So when we create a power tree, we have to start someplace. Let's start with the input power. We need to know what that looks like. So we click on this, and then we can place an instance on our Power Planner window. The default is to allow you to place more of the same thing on the page, so we can put 2 or 3 or 4 of these if we want. Since we only have one input on this design, I'm going to stop there, which you do by pressing the escape key. So there's our power input. If we double click on this, it opens up a little window over here. And in the window, there are some parameters that we can enter. So I might call this input. All of the stuff that goes in these windows can be anything you want. The numerical values need to be numbers, and the tool will use those eventually. But so I can call this input. It's 12 volts. And I'm going to put an arbitrary number here. Let's say 5 amps. So let's say we have a 12 volt input supply and it can support up to 5 amps of current. So we put that in there. Now this reads input and we see the 12 volts there. So what's the next thing we do? Well, we need to put some power converters on there. So I find the icon that represents power converters. I click on it. And now I can place these. So there's 1, 2, 3. So let's put 3 power converters there. They all default to 2 volts out and an efficiency of 90%. And then we need some loads. Actually, I'm going to add one more converter in here. We remembered that we need an LDO for the SerDes circuit. So the LDO is going to be treated differently from a regular power converter because the LDO efficiency is not arbitrary and it's not the same for different configurations. Remember, LDO efficiency by definition is output voltage divided by input voltage. Doesn't matter the current, nothing else matters. So we have a specialized device called an LDO that'll be treated in such a way that it'll reflect what an LDO actually does. So let's put that in there. And then we need some loads, the different parts of the circuit that are going to use power from these different power converters. So here is the icon for the loads. So we'll populate these here. Okay, so we have 4 converters and 4 loads. And I don't like the spacing here, so I'm going to move these over. And like with many drawing tools, you just select a group of devices and you can move them all together. So there we go. Now, I'd probably like to put something more meaningful in the boxes so that it starts to look like the table that I have. So let me start with the load. So this first load is going to be the top one from the list, which was the housekeeping supply. So I can double click on this load and it opens this window. And now I can just type 5 volt housekeeping. Okay. And the load for the housekeeping supply is only 0.5 amp. So I enter 0.5. And there's our housekeeping load. Now, we can't see all of the text, so we can just make this box bigger so it all shows up. So there we are. 5 volt housekeeping supply draws 0.5 amp. The next one might be the standby, 3.3. So 3.3 volt standby. And this draws from my table 2 amps. Okay, and again, we'll make this bigger so the text looks nice. Okay, and we can do the same thing for these other rails. This might be the external I/O. And then the last one, this is the SerDes load, so I'll type SerDes in here. And this is going to draw 3 amps. Okay, I'll give these converters some names. Call this buck 1. I haven't picked a device yet. This is for the housekeeping supply, so this is 5 volts. And we need at least a half an amp, so I'll put in 1 amp for the output voltage on this rail. And now notice that the little indicator for the voltage here now has changed to 5 volts. I'll call this one buck 2. And this will be for the 3.3 volt standby, which we said was 2 amps. So I go in here and 3.3 volts and 2 amps. And then buck 3 down here. This will be for the external I/O. That's 3.3 volts. And that one needs 3 amps of current. Okay, so we annotated this block diagram a bit. Now we need to connect things up. And the tool you use for connecting things is this icon right here. It's called draw wire. A wire means that there's an electrical connection from point A to point B. So we click on that, and then we click here and draw a line over to here and click again. When we do that, the line turns blue, and that means that we've made the connection from one end to the other. And so now we know that buck 1 will actually see the 12 volt input. So now we need to connect up the other ones. I like doing it this way because it makes it easier to make the connection up here. When we do that, you notice there's a little dot that's put on the place where those 2 wires connect. That's a convention you'll find in many schematic capture tools. It just reinforces that you've actually made a connection there. And so that now both of these buck converters are sharing the 12 volt input bus. Do another one here. There. Okay. So now the inputs are hooked up. Now let's hook up the outputs. And so I drew this one, but it doesn't quite line up with the input here. So I need to move this a little bit. Let's try that again. Draw a wire here to here. There we go. And then I'll connect this one. Click there. Click there. But this one, so I need to align that better. There we go. There we are. Same problem there. Go. And now let's draw a wire there. Okay. So now we've got all these parts hooked up and input, output, and the loads. And so now to analyze the performance of this, there's an icon up here that's called Calculate Power. And when we click on this, the tool will do all the math, add up all the currents, follow it back upstream to the input supply, and tell you how everything's doing, including how much power is being dissipated by the various blocks, the various converters. So let's click that and see what we get. And so we run this. Now you notice all the little annotations around each block. And there's one here that's in red. that means there's a problem there. Something isn't matching what we put in for that converter. So let's figure out what's going on there. And I look over here and I see, oh, this is the external I/O. It should be 3 amps. And it looks like I inadvertently put 15 amps in. That's the default, so maybe I forgot to type it in. So let's correct that, put in 3 amps. And now that reads 3 amps. And we can run this again. Okay, so we got the 3 amps corrected, but we still have a red flag here. So let's see if we can figure out why. So we open this up. Oh, the maximum output current from this rail is 3 amps. But if we look here, we're drawing 3 amps here in the external I/O load, but we're also drawing current through the LDO, another 3 amps, and that's why this says 6 amps. So the tool helps guide you to places that are problems where something is exceeding what you've specified. And I also notice down here under the LDO, the efficiency is only 30%, which is quite low. And it's telling me that the power loss, and let me zoom in a little bit here so you can see that better. The power loss in the LDO is 6.9 watts. That's a lot. That's going to be more power, more heat than this package can get rid of. And so this is going to overheat. So we have to take a look at why is that happening. And I see a couple errors here. One is that this LDO should be 1.5 volts, not 1. And the other is that I have the input coming from a 3.3 volt rail. And that means that there's a large drop between the input and the output, and that's why the power dissipation is so high. So let's correct that. So the first thing I'm going to do is cut the line here so the LDO isn't being powered by 3.3 volts. While I'm at it, I'm going to correct the voltage here. So this output is 1.5 volts, not 1 volt. And then, since I know I need to add some more converters anyway, I'm going to copy and paste another set in here. And this one I'm going to call buck 4. And the output for this one will be 1.8 volts. And so that's going to, we have several 1.8 volts on the board. So let's see, the CPU I/O, that's 1.8 volts. And this is a 10 amp converter. And now this will be CPU I/O. So instead of external I/O, 1.8 volt CPU I/O. And that's going to draw, what did I say, 5 amps. All right, so let's connect this up. Connect this there. Connect the input to the LDO here, and the input to the buck here. All right. Now let's run this again and see what we get. I'm going to move this up a little bit so we can zoom in. Okay, now there's no more red, so we're not violating anything anymore. Here, looking at the LDO, we see that the efficiency is much higher. It's 83%. And the power dissipation is 0.9 watts. That's what we estimated up front that it would look like. And that's because we only have 300 millivolt drop from input to output times 3 amps. 300 millivolts times 3 amps is 900 milliwatts. And now stepping back and looking at the big picture, we see how all the information from loads, the converters, and their efficiencies rolls it all up to here, and here's our 12-volt input supply, and we'll need a total of 3.09 amps to power this part of the power tree. So you can ask, does your 12-volt input power supply, can it provide something like 3.5 amps or something greater than 3.09? And if the answer is yes, you're good. If the answer is no, then they need to get a bigger power supply. So this is how we get started with the power supply design. And I'll save this now. I'll call this Power Tree 2. And when rating power for things like resistors, my rule of thumb is include something like 50% headroom. So if I'm going to dissipate 4.5 watts, I probably want a resistor that can handle about 9 watts, just so that I'll be certain it won't ever overheat, even if the airflow is lower than expected or whatever. It's possible to do something like put 3 or 4 resistors in series to make up that dropping voltage, and now each resistor is lower power because each one is only dissipating a quarter or a third of the total power. But it's still not that ideal. I would tend to use those dropping resistors and Zehners and stuff like that when you just need to nudge the voltage a little bit. So let's say this was a 2-volt rail on the output of the buck, and I do my calculations, and it means the power dissipation is more than a watt. So that's maybe a little more than I want. So I might put a small resistor in there to drop it down from 2 volts to 1.8. Now it all kind of plays together well. If the only thing that additional buck is doing is powering the LDO, well, then, there aren't a ton of requirements on that buck. So maybe it can be small and, it doesn't need to be the fanciest buck converter in the toolbox. But you need something to get it down to where the LDO isn't going to get too hot. Okay, so I've saved this. I cheated and did the power tree ahead of time. And let me see if I can find it. There it is. So this is the full power tree that I put together. And it probably took me an hour to put this together, just thinking about each regulator and, choosing individual parts for it. Here's that LDO that we were just talking about, and I do have it running off the 1.8 rail, so that worked nicely. And here's that DDR termination regulator, and it's running off this 3.3 volt rail, so it's happy. And we can go ahead and run this and take a look. And this looks pretty good. The overall efficiency is 88%. That's a pretty high number. I should be happy with that. And you notice when we rolled everything up, now that input power is higher because we've got more regulators involved, including these 2 down here that are the core supplies, which is a fair amount of power there. So the total is about 8.8 amps. So that 12-volt power supply probably ought to be capable of 9 or 10 amps to make sure that everything will work smoothly. Okay, now you'll notice I've entered efficiencies into the power tree for each of the power converters. And so a question is, how do you find out what the efficiency is for a particular converter in a particular configuration? And so I'm going to step back to my PowerPoint here. One quick and easy way to get the efficiency is to look in the data sheet. And this is the efficiency curves from the LT8640A data sheet. And it just so happens 12 volts in to 3.3 volts out, they've got a set of curves for that. And that's great because all you got to do is read the number off the curve and you're good to go. A couple of things to note. First off, there are 3 curves, a green one, a blue one, and a red one, and they represent different switching frequencies. So this gives us an indication that as we move the switching frequency higher, we take a little bit of an efficiency hit. And that's because switching losses rise with rising switching frequencies. Switching losses are a particular type of loss that happens, and they result from having to, let's say, charge up and discharge parasitic capacitances like the gate capacitance on a MOSFET. So your switches are MOSFETs. You have to drive the gate up and down to turn them on and off. You have to charge up and discharge the gate capacitors or capacitance on those MOSFETs. The faster you go, the more often you have to do that in a given unit of time. And so that takes up some extra power at a higher switching frequency. So right there, you can think, oh, so if I need to increase the efficiency a little bit, maybe running at a lower switching frequency will help. And in general, that's true. It will. Another thing to notice is that these curves, you notice how their highest efficiency is at some fraction of the maximum output current. This converter can deliver up to 5 amps. And so the efficiency curve shows from a half an amp up to 5 amps. But you notice the peak is around 2 or 2.5 amps. That's where the efficiency is highest. So if you have an application where efficiency is one of the most important criteria, one approach might be to use a converter that has more output current capability than you actually need. So if you needed a converter to deliver 2.5 amps, if you choose a converter like this that actually can deliver 5, now you can get better efficiency at 2.5 than a converter that was designed only for 2.5 amps. And the trade-off there is size and cost, because the 5 amp converter is going to be a little bigger than the 2.5 amp one, and it's going to cost a little more than the 2.5 amp one. But if I'm very power limited, I need the highest efficiency possible, that's a good way to help with that scenario. Okay, in our little power tree, we're using the LT8640 for 2 rails, a 3.3 volt rail and a 1.8 volt rail. So let's go to the data sheet and see if we can find an efficiency curve for 1.8 volts. So here's the data sheet for that part. We see an efficiency curve here on the front page. That's 12 volts in to 5 volts out. That's not what we need. So we go down a little further in the data sheet. Here's the 12 volt in to 3.3 volt out efficiency. That's the one we just looked at. But there are no efficiency curves showing 1.8 volts out. So that's a little disappointing. By the way, here's just another curve that reinforces that how the switching frequency and efficiency are related. We see that above about 1 megahertz, there's a linear degradation in efficiency as we go up in frequency. So what do we do for 1.8 volts? Well, we can use LT PowerCAD to give us an estimate of the efficiency. And so I'm going to now go in and look at how do we get that information. So we start with the LT PowerCAD startup page, and I click here to bring up the LT PowerCAD power supply design tool. So I click on that, and the first thing that comes up is the LT PowerCAD part search. This is the mechanism where we can decide which part we're going to use for a particular rail. And the way this works is you enter in some parameters over here and here for what you're trying to do. So I'll enter in the input voltage range. So the minimum might be 11.4 volts. The nominal is 12. The maximum might be 12.6. That's 12 volts plus or minus 5%. We have one output, The output is 1.8 volts at 5 amps. So I enter in 5 amps here. Now, it also can help to select a converter type, just so it doesn't come up with such a large list of answers. And since we know we're looking for the 8640, that's a monolithic part, I'll select monolithic. And here in the little graphic, it shows the controller and the switches inside the blue box, indicating that the switches are on chip with the controller. And then we click Search Parts, and now the tool will start looking through its database for parts that meet these criteria: the input voltage range, the output voltage and current, and that are monolithic. And this takes a little bit because there are hundreds of parts in the database, and the tool has to go through each part and evaluate whether or not it's a candidate. And bingo, there we are. So this is a list of parts that all potentially could do this rail that we're trying to design. I notice here, this is the 8640. I sort of had an inkling that was the part we were going to want to choose. And so if I click over here on this icon, it will open up the design tool for that particular part in this configuration. So we click on that and give the tool just a couple of moments to get all the data from our search tool and open up the power design tool. And here we go. So here is the power design tool for the LT8640A. And the comments here tell you that this is a 42 volt rated part, so the input can be up to 42 volts. It has 5 amps of output current capability, and it's a monolithic micropower silent switcher. And the tool has configured all of the specs that we put in up front. Here, the input voltage range. It has chosen a switching frequency. We didn't give it one, although we can if we want to. So the tool chose one. It's going to use about 800 kilohertz. And here's our output voltage, 1.792 volts at 5 amps. Now in this tool, there are a bunch of fields for different parameters. And there are blue fields and yellow fields. The blue fields are fields where you can enter information. It can be anything from a part number to a value, etc., or a part vendor. And in the yellow boxes, those are calculated by the tool, so you can't change those. An important parameter to be aware of, if we look over here in the inductor section, the tool chose an inductor, but a critical factor in choosing this inductor are things like the input voltage, the output voltage, the switching frequency, and we need to know what the ripple current needs to look like. So what is the ripple current? In an inductive-based switching converter, the switches toggle up and down between V-in and ground, and when the top switch is on and the switch node is connected to V-in, remember the current rises in the inductor. When the switches change state, the switch node is pulled to ground, the current falls in the inductor. And so that peak-to-peak current waveform is called the ripple current. And the rule of thumb for doing switching converters, particularly ones that are current mode control, where the controller is monitoring that inductor current every switching cycle. So cycle by cycle, that inductor current is always being monitored. The current needs to be large enough so that there's a big enough signal for the controller to evaluate. If the ripple is too small, then that signal inside the controller, the voltage on that signal is very small, and noise can get in and make it hard for the controller to pick the same point every cycle. The controller turns the top switch on, the current will ramp up to a peak value, and that's what determines when the switches change state. if that signal is really tiny, you won't be able to pick the peak at the same spot every time. And what this results in is jitter on the switching waveform, and that's undesirable. It leads to noise artifacts in the output and things like that. So the ripple current is a critical parameter. The default is around 50%. That's a reasonable choice for ripple current, and it's 50% of the maximum output current. So for a 5 amp converter, you want about 2.5 amps peak to peak of ripple current in that inductor. So given all that information, the tool calculates you want an inductor value of somewhere around 0.75 microhenries. 0.75 is not a standard value, so the tool picked a 0.68 microhenry inductor, which is pretty close. And then the tool has also filled in the resistive divider. This is the divider that sets the output voltage. And it's picked a value for the oscillator frequency resistor, because this is what sets the switching frequency. So that's all preset for you. Now, across the top here are tabs. This is like tabs in an Excel spreadsheet. So we can go to the second tab called Loss Estimate and Breakdown. And here we get an efficiency curve for this converter running in this configuration. V out is 1.8 volts essentially. And this is what the efficiency curve looks like. So out here at full load, the efficiency is about 86.7%. And the power loss is 1.38 watts. Now over here, this pie chart will actually show you where the power losses are. So the yellow represents the total IC losses. These are the losses in the chip itself, the switches, etc. The green section is the inductor, what we call DCR loss. That's the DC resistance. So the inductor consists of some magnetic material and a wire forming a coil, and that wire has resistance. So when you pass current through that wire, there's a voltage drop and there's some power dissipation. So that's what the inductor DCR loss is. So now we can look at this and say, okay, our efficiency is 86.7%. We now go back to our power tree, and here I entered in 87% for that rail. It doesn't have to be 100% completely accurate, but it needs to be in the ballpark so you get a sense when all the math trickles through of what you need at the input for power. Okay, I'm going to stop there. Thank you all for coming and attending.